Okay, so last time we introduced the fundamental group, so let me just remind you briefly, because what we're going to do today is we're going to use this object we've introduced, the fundamental group, to prove some really fantastic classical results in topology. And what you should think is that we spent all this effort in previous lectures building up this thing, and now we're going to use it. Now that we have this machine, we're going to use it. So the fundamental group is somehow classifying, what it is it's the set of your equivalence classes of loops. So set of equivalence classes of loops up to homotopy in some space, up to homotopy with a fixed base point. And so, really you should have a couple examples in mind, and one example should probably be something like R2, although it's the same for Rn of any n, so let's just say Rn, where the fundamental group of Rn, let's just think R2 is kind of the canonical example, is if you have some base point, then any loop you might have can be shrunk down via homotopy. A homotopy is just a series of shrinkings, a little movie, to the single point. It can be shrunk down to the constant point. And for any loop, you could have some other loop that's doing some weird stuff, but you could play a story of that shrinking down to the base point too, right? And so the fundamental group of Rn, this is trivial. So I'll often write this as 1 or 0. I'll probably prefer the notation 0, but you should think that's the group with only one element, a single trivial element. So this is trivial. This is the trivial group. If you prefer to use 1, that's fine. It's just a group with one element inside of it. Any two loops can be deformed to the constant loop, meaning any loop could be deformed to another loop via this movie we call a homotopy. By way of contrast, pi1 of S1, where S1 is my notation for the circle, it has no thickness. I just drew a little bit of thickness so we can see the loops on it I'm about to draw. Pi1 of the circle is not trivial, because you might have a loop like this loop that wraps around once, and that loop can't be pulled down to just the base point, because it would require leaving the circle, going into the disk. But S1 is just the boundary here. So you can't shrink it down to just a single point. And so this guy has things that are beyond the trivial guy. There's the constant map that just sits here. There are things equivalent to the constant map, like go out for a little bit and come back. If it does that within the circle, that can be shrunk down to a single point. But you also have the guy that loops around once. And then you have other guys too, like the guy who wraps around several times, 5 times, 6 times, whatever that was. Or you have the guy that wraps around 1,000 times. Or that wraps in the opposite direction, the negative direction, 12 times. And you end up with a loop corresponding to each integer z, right? And so this was the big contrast. Some things have trivial fundamental group. Some things have more complicated fundamental group, like the circle, which has fundamental group z. We're going to use this fact today, just this fact, to prove some really beautiful theorems. And so we'll come back, we'll talk more about the fundamental group in the future, but now we're just going to use this basic fact that these guys have different fundamental groups in order to prove some beautiful classical results. And the first result is called Brouwer's Fixed Point Theorem. So have you heard of Brouwer's Fixed Point Theorem before? Anyone familiar with this? The basic idea of Brouwer's Fixed Point Theorem is if you take a disk, okay, it's square, but it's a disk, it's equivalent to a disk, and you have some way of mapping this disk onto itself. So here's a second identical copy of the disk. And we're going to want to send every point inside the disk back inside. So one way to do that would just be like 180 degrees rotation, right? Then the claim of Brouwer is that one point stays the same, at least one point. What point stayed in the same location when you just rotated it around? The center point, right? The center point is still in the very center. But you might think, well, there are other ways to map it onto itself. As long as it's a continuous mapping, he says, at least one point will stay the same. So the extreme example of this is one way to continuously map it into itself is just to like crumple up and just place it on top. That is a continuous mapping from the disk into the disk. And what Brouwer's fixed point theorem is telling you is that at least one point is a same place, is exactly over where it was before. It might be hard to figure out where that point is, but there's at least one that's in exactly the same place. So in mathematical language, that's saying if you're given some continuous map from the disk to the disk, there exists a fixed point. So by fixed point, I just mean some point, so that f of that point is that point, right? Okay. So we want to prove this. So how might we prove this? I don't think it's obvious. Yeah. I'll just ask you, I mean, what proof strategy would you use? My claim there's always a fixed point. What's one way we might go about thinking about this? Well, let's see what bad stuff would happen if there isn't. So this is not really a guide to how to prove it, but maybe it's a first step. I remember I was talking to someone recently about like a research project and like about proof strategy, and he's like, oh, let's do proof by contradiction, as if that gives you the proof. Like, well, you still have to do the proof by contradiction, right? But at least we have a starting point, right? So let's suppose not. Let's suppose that there is no fixed point. So all that's telling us is that every point x, whatever point x you pick, is going to get sent to some other point f of x. The next step I don't think is at all obvious. Given that construction, what we can do is we can define a new function, where the new function is going to be formed by taking a ray from f of x to x and seeing where that ray hits the circle. And I'm going to call that r of x, because it's the end of the ray. So we can define r to be a map from the disk d2 to just the boundary of the disk, the circle, S1. Note, R is only well defined because x and f of x are different points. If there was a fixed point, if x was equal to f of x, we wouldn't know how to draw the ray, right? It's only because f of x is a point different than x that when you connect f of x to x, you can keep going and you can figure out where it hits. If x is equal to f of x, it's not at all obvious how you should draw this ray. And so we can only define R given this assumption that there are no fixed points. And now we're going to say that this map R shouldn't exist. abomination, right? This shouldn't exist. And that should be our contradiction. Okay. So what's so bad about R existing? Well, first observation. Observe. If you take some point that's already in the boundary, some y, that's in S of 1. So let's say y is my point right here. What can you tell me about R of y? Well, let's first think. Here's y. I'm going to apply f to it. I have no idea where that's going to end up. Maybe f of y is over here. Maybe f of y is somewhere totally different. But wherever f of y is, what is my ray going to look like now? My ray will just end at y, because it's already on the boundary. So R of y will be equal to y. So for all points in S1, R of y equals y. So what is this map? This is a map that takes the disk and maps it onto the boundary, but that leaves all points on the boundary fixed. This is called a retraction. We talked about this briefly, what, first maybe second week? This is a retraction. Of D2 onto S1. And I'm going to claim that these kinds of things shouldn't exist. You shouldn't be able to retract D2 onto S1 in this nice continuous way. I mean, this is a continuous function. This is a continuous function. If you varied f a little bit, then your point here is going to vary a little bit as you move x. These guys vary. Since f is continuous, as you move x, this will vary by a little bit, and the point will end up close by. So since we're assuming f is continuous, this ray is continuous as well. And so R is actually a continuous retraction. It's a retraction, it's a continuous map. So what's the problem there? The problem is, the whole reason that the fundamental group of S1 was Z was because you couldn't poll the guy that went around once. Let's give him a name. You couldn't take this loop that goes around once. I'm going to call that loop W1 for winds around once. There was no way of taking that loop that winds around once and deforming it into the loop that just stays at 0, the constant loop, the loop that winds around 0 times. They're not homotopic, right? But if there was a retraction, there would be a homotopy. And here's the homotopy. Note, W1 is homotopic to W0 in the disk. In the disk, there's a way of deforming this guy to that point. We can, let's give this homotopy some name. Let's call this like, I don't know, H of t. And you can even give me an explicit formula for H of t if you like. Here's my S1. Let me thicken up S1 a little bit so we can think of the loop as living inside of S1. Here is my W1. Here's W1. And then there's a homotopy that shrinks W1 to W0, which just sits at that constant point. And what the homotopy looks like is in the disk, you just start shrinking him a little bit, right? So there's a clear homotopy inside the disk. And I'll call that homotopy H of t. So here I'm trying to draw a series of pictures for h of t. So maybe this is like, h of 0, this is h of 1, here you're like h of 1/2, right? You're moving between them. No problem yet, except if h of t is a homotopy in the disk, then think about what happens if you compose h of t with this retract. This is now a map that begins, well, h of t is a map that's going from 0, 1 into the disk, but then R maps it into S1. Which says R of h of t is going to take this homotopy inside the disk, and each one of these moves to somehow a loop inside of just S1. This is now a homotopy. R moves the disk into S1 in a continuous way. So this is still continuous. A composition of continuous map is still continuous. It's now a continuous, it's continuous, so it's a homotopy. It's a homotopy in S1 from W1 to W0. From W1 to W0. That is, we just showed that W1 is homotopic to W0. But that we know is false. In fact, by this argument, you'll be able to show any loop around S1 can just be homotopic to the constant loop. If this were true, this would actually mean that pi 1 of S1 is just the trivial group. But we've shown before that's not the case. So if there was a retract, a continuous way of mapping the disk into S1, then homotopies you can do in the disk now become homotopies within S1, killing the fundamental group of S1. Are we comfortable with the structure of that proof? Now, maybe you're like silently thinking, well, there is a retraction of D2 onto S1. I mean, like, just take D2 and just like from the center, send every point to wherever that ray points, you know? Like send this point here, send this point here, send this point here, send this point here. Why isn't this a retraction? Where does the middle point go? Right? And it's like wherever you put the middle point, it's going to introduce something that's no longer continuous. If you punctured out the middle point, then you can do this. So if you think of the disk minus a point at the center, subtract the center point, then that can be deformed onto S1. Actually, this is a homotopy equivalent space to S1. So this has the same fundamental group. But if you have the whole disk, you can't do it because you have a discontinuity at the center. Okay, cool. This is, I think, a really cool theorem. It was one of the early triumphs of algebraic topology, or what came to be known as algebraic topology, when Brouwer proved this in 1910, I believe it was. But then Brouwer started meddling in some philosophy. And he was quite bothered, in part by proofs like this, that this proof told us there was a fixed point, but it didn't give us a way of finding the fixed point. Here, in this example, we said that there should be some point that stayed the same, but good luck finding it, right? Maybe you could, but good luck. So that is to say, this is a non-constructive proof. So this was a proof by contradiction, and so by proving it by contradiction, it was a non-constructive proof. Meaning we didn't actually construct the fixed point. The other proof strategy would be if you can come up with an algorithm that always helps you find where the fixed point is. We didn't do that. We just proved that if there wasn't a fixed point, bad things would happen, so therefore there must be a fixed point. This bothered Brouwer, and so he, in time, came to accept a position called constructivism, which essentially says we only accept constructive proofs. he came to reject proofs by contradiction. What's going on behind the scenes here is a proof by contradiction relies upon something called the law of the excluded middle. We just showed if there's not a fixed point, bad things happen, therefore there must be a fixed point. But that relies upon this principle of law of excluded middle. Constructivists reject this, they reject proof by contradiction, and then Brouwer had to reject his own theorem because he wasn't able to find a constructive proof for it. So, the good news is that while there still are constructivist mathematicians, everyone recognizes them as a bit kooky. So, you don't have to worry about this. If you meet one at a conference, smile and shake their hand, but just kind of keep your distance. And we're going to maintain proof by contradiction as a legitimate proof method. But some mathematicians have, and maybe at some other point I'd be happy to talk more about this, philosophical objections of why they want constructive approaches. Okay, historical aside. Let me give you a second theorem, another classical result. And we're going to, in some ways the proof's very similar, that was going to use these facts by the fundamental group to prove this. So this is the Borsuk-Ulam theorem. May have heard of this one before. And so first I'll state the theorem, and then I'll give you a nice interpretation of it. The Borsuk-Ulam says if you have a continuous map, everything here needs to be continuous. Give it a continuous map from the sphere to R2. And this actually generalizes to any dimension n, n greater than or equal to 1. But if you have a continuous map from the sphere to R2, then there exist antipodal points, a pair of antipodal points on the sphere such that, so when I say a pair of antipodal points, you should think like x and something in the opposite of x. So I'm going to note that as negative x. If you think of, for instance, as your unit, is your sphere being your unit sphere, then some point x would represent some x1, x2 as your coordinates. Didn't fit. x1, x2 as your coordinates. And if this is like the unit sphere, so if this is 0 at the center and we're going 1 in every direction, then the antipodal point would be right down here. It would be the point just negative x, which is the points negative x1, negative x2, right? Okay. Sorry, this doesn't make any sense at all. How am I describing my coordinates? You could think of this as being embedded in R3, and then your x could be some x1, x2, x3, where the magnitude of this is 1. Okay, then negative x would be negative x1, negative x2, negative x3, or maybe of some other coordinate system. But I just use negative x to denote the antipodal point from x. Another way you can define a antipodal point is if you take the line that goes through that point and the center, then the other place where that line hits the sphere will be the other antipodal point. There are cool websites where you can find the antipodal point on the Earth of the point you're at right now, and I'm pretty sure ours is somewhere in the ocean. Okay, so there exists a pair of antipodal points such that f at 1 is equal to f of the other. So let me give you an interpretation of this, and hopefully you find it quite surprising. Here is my S2, the surface of the Earth. Sorry, flat earthers. Continuous function from S2 to R2. We just need two values that vary continuously on the surface of the Earth. And so classically, you might think of something like temperature and pressure, or humidity, or whatever you want. Let's just do your temperature. and your barometric pressure at each point. As you move a little bit, your temperature changes a little bit, right? But it's a continuous change of temperature. Then, what this is claiming is that there exists on the Earth two points, like, you know, a pair of antipodal points, one point complete opposite side from the other, that have the exact same temperature and the exact same pressure. That's kind of surprising, right? Or you pick any other two metrics. Maybe it's temperature and humidity. Then, you know, you would have 2 points, antipodal points that have the exact same. This is guaranteeing that there exists 2 points, opposite ends of the Earth, with the exact same pressure, exact same temperature, and exact same humidity. We're clear on what the theorem's saying? Counterintuitive, right? Surprising. We just learned something about the world. Was there a question? Did I say something silly? What? Yeah.
But this assumes that you can actually define a return pressure for every single point down to like.
Yeah. So we're assuming that these are continuous maps. So at every point you'd be able to say, you know, at this point the temperature is in Fahrenheit 72, and at this point it's 71.98 or whatever, right? Like so it is, you know, that is an assumption. You're right. But so what are you thinking? Like the space is not discrete or something? Like the space is not continuous, it's discrete. Wow. So if you zoom in, so like, you know, if you have these concerns that as you like zoom in at some point, like things become discrete, then you can just say, well, up to some really good approximation, it's continuous. Like you can model the Earth, and in the model you will have opposite points, and then up to like, you know, some crazy approximation, it's in reality, right? But I prefer to think we live in a mathematical universe where, you know, we live in the model.
So what's like,
yeah.
Any two physical continuous variables?
Anything continuous, yeah. Any continuous function to R2. So you just pick any two things that vary continuously across the surface of the Earth.
So what about like light from the sun? Wouldn't that like...
If it's continuous, I mean, I'm a little bit concerned about there being like some obstruction that blocks, so you have like high intensity and then right next to it. No, but you'd still have diffusion of light, right? I guess like the...
points of the Earth is going to be day and night.
But like dusk and dawn would have the same intensity. Right, like, yeah. So that's good, yeah.
So does this apply for like any metric you use on the surface?
When you say any metric,
define antipodal points.
Well, just use this definition if you prefer, where you go from one point through the center, and where the line hits the other one's the antipodal point.
I guess
I was just trying to explain the notation for negative x, but it is only really taking the negative if you think it was being embedded in R3 or whatever.
Okay, so it doesn't matter if it's perfect sphere, and you can have a squashed sphere and then just put it and then define it.
You're concerned like if your square is a little bit squashed. Well, that isn't going to really matter too much because what you can do is you can map the squashed sphere that maps onto a sphere, right? Like you can idealize the sphere first, and then it holds. And the points on the squashed sphere map 1-to-1 to points on an idealized sphere.
So if you map it differently, so you squash it differently, then you'll have different antipodal points that apply?
Not necessarily, because the function would still, you know, at each point have its values. Okay, I don't want us to get too worried about like the Earth is not a perfect sphere, or maybe is temperature really continuous. Let's just, you know, imagine the Earth is a sphere and we have these continuous functions, and then you can worry about, you know, in your own time, in the real world setting, how much this idealized fact carries over. But you should be in awe of this. Okay, maybe what I should do first, I don't know if we have time for this or not, but I'll do it anyway, is convince you that the lower dimensional case of this is actually not that hard. So smaller theorem, lemma, I don't know, I'll call it a theorem still. But like this is something you can do in calculus, is if you're given a continuous map from, here I'll just call it, I'll still call it F. From S1 to just R1, the real numbers, then I want to say the same thing. Then also there exist antipodal points. And so, like, you should convince yourself of this smaller fact. And maybe I'll just take a few seconds to help you think about it. So here I think about, as I go around, I have my points x, and on the opposite side, negative x. Wherever x is, you have negative x on the opposite, on S1. I claim this actually follows from calculus. So how would you approach this? Oh, yeah, very good. Which theorem? Mean value theorem. Okay, I was thinking of the intermediate value theorem. Okay, intermediate value. It's been a couple of years since we've done calculus, right? So how would you set this up formally? Do you remember? Like, what's the trick to use intermediate value theorem? Well, you have these two values. You want to show they're the same. So how do you move from having two functions showing they're the same to having one function? You can just set up a new function, call it the difference function, d of x. You can define to be f of x minus f of negative x, right? And we just want to show that somewhere this value achieves 0, somewhere it obtains 0. But this is not too hard, because if you start off at a point up here, if this is your x, well, then you have three possibilities. One is d at that point is already 0. If it's 0, we're done. Another possibility is that d at that point is positive. But if d at x is positive, what can you tell me about d at negative x? D of negative x is just f of negative x minus f of negative x, which is f of x. And that is just the flipped of d of x, so that's just negative d of x, right? So if your d of x is positive here, it must be negative here. But since our function f is continuous, as we move around, this d of x is also continuous, since it's just made up of continuous functions. So this is a continuous function. So even if your d of x wasn't 0 at this point, say it's positive, then that means that at this point, your d of that point must be negative. Hence, by the intermediate value theorem, there must be some point in between, I don't know what, some point, we'll call it c in between, where at this point, d of the c is 0. So that's just a calculus fact, right? These are all real valued functions. Okay, so you can use this calculus to prove this is true in the one-dimensional case. But let's say we want to prove it in the two-dimensional case. And it also holds true in higher dimensions as well. For that, we're going to use something similar, but we're going to set it up in the language of abstract algebra. So let me come back over here. So we're trying to prove this fact. So here we're trying to prove Borsuk-Ulam, and here's my proof. First, I'm going to do proof by contradiction. Suppose not. So what I'm now supposing is that f of x is always distinct from f of negative x. The reason I'm going to suppose that is because now I can define, just like before, a kind of difference function, f of x minus f of minus x, but I can divide that by the magnitude of f of x minus f of minus x. Since these are never equal, this bottom is never 0. Since we're supposing these guys are never equal to each other, right? This is only well defined if we suppose that antipodal points are always distinct. So if we're supposing these are distinct for all x in my S2. Okay, so let's think about what G is. This G is a map that takes in values x, takes in values in S2, and spits out, well, f was something in R2, so these are values in R2, but when you define it by its magnitude, it's now going to be say S2? S1. S1. Right? So like here's the picture you should have in mind. Here's your R2. F of x minus f of minus x is some point out here. It's an R2. But when you divide a point by its magnitude, you just come down to wherever it is unit distance away. Right? So all points get sent to something on this unit circle. On this unit circle. Okay, so a classic move to move points to the unit circle is just to divide by the magnitude. So now G is a map from S2 onto S1. I'm going to define one more map. I'm going to define the map L to be a map that's going to be sending points onto S2, but just onto the, right, just onto the equator of S2. So if I think of this as being my S2, then I have this equator of S2. So this S1 is the equator, this S1 here is the equator of this S2. And I'll send points onto there just to loop around that equator. So if you think of this S2, for example, as living inside of R3 in three-dimensional space, then I can just define my L to travel around this equator by giving it some parametric description like cosine of, okay, it needs to go all the way around in time 1, so I think that would be 2 pi s, then sine of 2 pi s for my x and y coordinates, leave my z coordinates 0. I think that does it. That would be a parametric description of going around the equator. That's what my L is. Okay, so putting this all together, I have the unit interval 0, 1. L maps that onto this equator. And now I have a map G that sends all of S2 onto S1. But in particular, I could just focus on sending this equator onto S1. So I can just look at what G does to the equator. And if I think about the composition of these two maps, so I'll define a new map. Let me call this map H. H is going to be the composition, so first do G and then do L. So H is a map that sends things from the interval 0, 1, places it onto this equator, and then maps the equator, that point on the equator, onto the unit circle. So H is a map from 0, 1 onto S1. Okay, we have a lot of maps going on here. Are you okay with how we set everything up? Just how we define these maps. Because what I'm going to do now is I'm going to argue bad things happen. We're going to get our contradiction. Okay, a few observations. Note. What is g of negative x? Well, the bottom's going to remain unchanged. The top is f of minus x, now minus f of x. So it's just flipped, it's the opposite, right? So f of minus x, of g of minus x, is negative g of x. Are we happy with that? So in our picture, I'll draw one more time. Sorry to draw this so many times. So in our picture, we first have this map L. That's just sending this guy onto the circle, which is the equator. And then we had my map G, which is sending him onto a copy of S1. Just whatever G looks like. We don't know what G looks like because we don't know what the function f is. But whatever G looks like, it's sending that circle somehow onto here. We know that g of negative x is equal to negative g of x. So that means in particular, if you have some point over here, that is your x, and you have some point over here, which is your negative x, then I know when those map over, my g of x and my g of negative x are antipodal points. Good so far? Okay. All together, we call this composition H. Let's think about what happens to H of S plus 1/2, where S is something between 0 and 1/2. So if my S is somewhere in the first half of this interval, then later on I have S plus 1/2. When I go from 0 to 1, I map all the way around here with a barometric equation. And the barometric equation moves around this equator at constant speed, right? So what can you tell me about S and S plus 1/2? They're antipodal, right? Like S would get mapped somewhere like here, and S plus 1/2 would get mapped somewhere here. So this is just showing that your L of S and your L of S plus 1/2 are antipodal points. So then, when you do G to your antipodal points, they remain antipodal. That's what we are saying here. So H of S plus 1/2 should be an antipodal point of H of S. So this is an antipodal point of H of S. One more picture. So here is my H of S, say. Over here as antipodal point, that's not going to the center, that's closer, is H of S plus 1/2, where my H was a map from the unit interval onto S1. Now, right now, this isn't concerning. Like, this is fine. This, all we're saying is this H just sends S and S and a half plus 1/2 to antipodal points. But what I want us to think about is, let's think back to our lecture on proving the fundamental group of S1 was isomorphic to z. And to do that, we had this lift that I'm going to try and draw right now. But I want to make sure I draw it going the right direction. I always get it wrong. So as I go around, I want him going up. So as I go around, I want, here we go. Here we go. Does that look decent? Recall, this is my real number line stretched into a helix so that it projects down onto the circle with some projection map P. But what we said is when you have a map into S1, we can lift it, some continuous map H, we can lift to some continuous lift H tilde, so that as you move around the circle, you're moving up the helix, right? In particular, if this is my base point, that base point will correspond to integer values, 0, 1, 2, -1, and so forth. Those all get mapped to my base point. Now, I want you to think with me. H of S, this point here, will lift to some point up here. We don't know where. And I put numbers here, so maybe that's going to bias you, but I'm just going to put it somewhere. I don't know where this lifts up to, but it lifts up. Maybe we can start it off at 0, start coming at 0, H of S, but I don't know. Maybe it's not there. Maybe it's down. I have no idea where it's at. He's going to lift somewhere. Let me just put some point up here to correspond to H, of the lift of H at S. Some point that's on top of this point. When we look at the lift of H of S plus 1/2, where's it going to go? Well, it needs to be some point on top of this antipodal point. So it might be here, it might be here, it might be here, it might be here. There's lots of possibilities. I'll just pin one down. I'm going to say maybe it lifts to something like this. The lift of H of S plus 1/2. You tell me, what is the distance in R from H of S, the lift of H of S, to the lift of H of S plus 1/2? What is the relationship between H of S plus 1/2 and H of S, the lift of these points? Going fully around the circle once corresponds to going up a distance of 0 or down a distance of 0 in the lift. So how are these guys going to be related? What's the distance between them going to be? If he had lifted to this point, what would the distance be? Just 1/2, that's right. If he had lifted to this point, that distance would have been 1/2. But we're not sure he lifted there. He could have instead lifted up here, in which case that total distance becomes 1/2 plus 1. So that would have been distance 3/2, right? Or maybe he lifts even higher, like this point, where the distance is now 5/2. In general, what's the relationship between them? They differ by some odd number over 2. They differ by some odd number, some odd integer divided by 2. Do you see that? Okay. Here's where we pull the rabbit out of the hat now. H is a continuous function. And so we can lift it as a continuous function. So these are both continuous functions, which means as you move S a little bit here, this one should also just move by a little bit. Meaning this integer shouldn't change as you change s. Because if you change the integer, you move this guy by a little bit, the other guy jumps down by 1. Right? You can't have that if it's continuous. So this integer must be independent of s, since it's continuous. Since h hat is continuous. This odd integer is something independent. So we can actually calculate exactly what it is. For example, we can figure out what is, we know that h hat of 1 must just be h hat of 1/2 plus whatever that odd integer is. Can I give this odd integer a name? What should we call it? M? Okay. M, where m is an odd integer. Plus m over 2. But then by the same reasoning, we know that h hat of 1/2 must be h hat of 0 plus an m over 2. So we get an m over 2 twice. So that just gives us an m. And now we have the distance from the lift of 0 to the lift of 1 is m. That is, if we look here, this point here is h of 0, that's my base point, but it's also my h of 1. And if we look at the lift of h of 0, h of 1, I don't know, maybe h of 0 lifts here, maybe my h of 0 lifts here, maybe my h of m lifts here, h of m lifts here, h of 1 lifts here, in which case my m would be 2. Okay, we said it was odd, so maybe he should go up a little bit more to like here. Maybe my h of 1 lifts here, in which case we see the distance between them is odd. Okay, so what is this m really? This m is just telling us, as I go around from h of 0 to h of 1, it keeps track of how many times I spin around up here. Right? That's what the m is keeping track of. The m is just keeping track of this distance between these. So that m is really just the winding number of h. How many times h wound around here, going from 0 to 1. So what this really means is that h winds around m times. H is homotopy equivalent to Wm. That's all we've shown. That's what we said. That's what this means. But since m is an odd integer, we know that W of m is not going to be the same as W of 0. So your h is not homotopic to the constant map. What we get out of this is h is not homotopic to a constant map, to the constant map W0. What's wrong with that? Well, come back. How do we define h? H maps this interval onto the equator and then sends the equator onto the circle. I claim there's a really nice homotopy from h to the constant map. Can anyone tell me what the homotopy is?
On the sphere in between, you collapse it down.
Good. Your homotopy from h to the constant map is you just start sliding this guy up a little bit, up the sphere. I'm trying to keep him at the same base point. You just keep sliding up the sphere and then down until he's at a single point. And at that stage, as you just move him there, at time 0, it's the full thing h. At time 1, it's collapsed to a single point. So when he maps over, he'll just be sent to a single point, the constant map. So this mapping here shows that h is homotopic to the constant map. Ergo, a contradiction. Okay. So you may think this was a bit tedious, and you may want to rewatch this proof or read through Hatcher to appreciate the proof in more detail, because the contradiction is a subtle one. But what we did is we both constructed a map that is both homotopic to the constant map, and yet we had an argument for why it's not homotopic to the constant map. And we used the same basic construction that we had used in proving that S1 has fundamental group isomorphic to Z. Right? And so the big takeaway, if nothing else, is that we use the tools of algebraic topology in order to prove this Borsuk-Ulam theorem, in order to prove this fact, right? Okay, so you can review the details of it, but hopefully you appreciate this big takeaway. In the last 5 minutes, I want to show one more corollary, one more theorem, but this theorem is just an immediate corollary of Borsuk-Ulam, and maybe we can prove it in like a quarter. It doesn't take much space at all. It's actually very fast to prove, but it's a very neat theorem. It's a nice little theorem. Another kind of geometric fact. So I'll write it as a corollary. Just like how I said this one is true for any dimension n, this corollary is also true in a higher dimensional space. We'll have to generalize it a little bit, but I'll just show it in the case of S2. So if S2 is the union of 3 sets, I'll call them set A1, A2, and A3, where these are closed sets. Very important that they're closed. Of 3 closed sets. Then, one of the sets, call it AI, I don't know which one it is. If AI in this class now. Maybe we can get some more funding, right? One of the sets contains a pair of antipodal points. So the way you should think about this one is if 3 alien species came and each claimed a portion of the Earth as their own. Here's like the Martians, and here are the Klingon. I'm mixing my universes right now. And maybe these portions overlap, maybe there's some disputed territory or whatever. And here's the portion of land that belongs to, what's another alien species? Come on, help me out. The who? I have no idea what you're talking about. Okay, so they all team up. Oh, the Ewok. The Ewok have the largest portion of land of all, for they are the most spirit alien species. This is not a very good drawing. But if each one claimed they'll split of land, then even if they overlap, 3 sets, if they close the whole Earth, if they cover the whole Earth, then one of those alien species, in this case the Ewok, have a pair of antipodal points. Okay, that's not really in the Ewok territory, is it? Well, one of these alien species, kind of hard to find these antipodal points sometimes. Here we go. Like maybe take Algeria and antipodal to that, it's probably something close to New Zealand. And was that the Ewok? I think it's the land of Ewok. Has a pair of antipodal points. That's not right. Okay, close enough. Somewhere on there, you have a pair of antipodal points. In general, if this is Sn, you need n plus 1 sets. So if you're in S1, you need 2 sets, right? And you should think about that really fast. Like S1, convince yourself like any 2 sets you make, any 2 closed sets, important they're both closed. Any 2 closed sets, play around with this. One of them will contain a pair of antipodal points. So, why is that true for S1? Well, how could you possibly avoid it, right? You might avoid it by trying to make one of your sets like this and then the other set like that. But those sets are no longer closed, right? If they're closed and you make both exactly half, then both contain the North Pole and the South Pole. So, and they don't have to be even like connected sets. You know, you can have one of your sets be you just color like all of these regions orange. You know, everything is covered by the orange as long as it's closed. And then the other set is, you know, you come in and maybe there's some overlap between them, maybe there's not. But the claim is even here, and as long as it's a closed set, like a disjoint union of closed sets is closed. You know, the orange set and the blue set, the claim is one of those contains a pair of disjoint. One of those contains a pair of antipodal points. And I don't know, can you see it? Which one contains antipodal points? Maybe this orange does, like right up here and down here, maybe? Kind of hard to see, but maybe like this orange point and this orange point antipodal. So however you do it, you know, whatever crazy way you do, as long as make sure both sets are closed, then, so you guys are in real analysis. So you know what, or you've taken real analysis. So you know what I mean by closed. Okay. If not, Google it, right? But I can tell you after class if you like. But closed is like, you can think the end is closed. It's not open, like an open interval, right? Okay. Formally, it contains all its limit points. Okay. So in the S1 case, maybe it's a little bit believable. Maybe not, it's still counterintuitive. But let me show you why it's true in the S2 case. And in general, it just follows from this for any dimension. So once you believe this in dimension n, you should believe this proof generalizes immediately. So the proof's very, very short. What I'm going to do is I'm going to define right. I want to define some maps. I want to define, let's say, some map D1, hope I have enough room here, from S2 to the real number line by the map that just takes any point x and asks how far away am I from region 1, from A1? What's the minimum distance, the infimum distance from x to y, the distance between those, where y is some point in A1. And that infimum exists because A1's a closed set. So this is why we need it to be closed. That is to say, you know, if you pick some point, maybe it's some point in the Klingon territory, you can ask what is its minimum distance to the Ewok territory? Or maybe that was the Martian territory. I don't remember at this point, right? So in here, you could pick some point in blue and ask what is its minimum distance to the orange. Or you could ask what is the minimum distance to the blue, and in which case the answer is just 0, right? So you can define this for D1, but you could also similarly define maps D2 and D3. So in general, you can define this DI to just set AI. So one for D1, one for 2, one for 3, asking how far away is a point from the region A1, A2, or A3. Then we have some map, now it's called big D, some map from S2 to R2 that's defined by x gets mapped to D1 of x and D2 of x. Are we happy with that? Okay. I said this was a corollary of Borsuk-Ulam. So what does Borsuk-Ulam tell us? By Borsuk-Ulam, we have a map now from S2 to R2. There should be a pair of antipodal points where this is equal. So there were some points x and negative x where big D of x is big D of negative x, which means both your D1 and your D2 are equal. So by Borsuk-Ulam, there exists some x so that D1 of x is the same as D1 of negative x, and d2 of x is the same as d2 of minus x. And now I just want to go through a few cases. Case 1, suppose this guy is equal to 0. What does that tell you?
The points are inside of the A as well.
Yeah, if d1 of x is 0, that means x is inside of a1. And if d1 of negative x is 0, that means that negative x is also inside of a1. And there you have antipodal points in a1. Maybe it's not equal to 0, though. If that one's not equal to 0, think about this one. Let's ask if this is equal to 0. By the exact same reasoning, if this is 0, that would be saying that both x and negative x are inside of a2. What if neither of them are 0? Yeah, if it's not 0, that means x is not inside of a1. And if this is not 0, this is saying x is not inside of a2. Or go, x must be inside of a3, and by the same reason, negative x must be inside of a3. So either one of these is 0, in which case they're both in a1 or both in a2. If they're both 0, then they're both in a3. So we have a pair of antipodal points. So else, I don't have room for it, but otherwise they're both in a3. Else, I'll just write else a3. Okay, we get the idea. Cool. So we saw, what, 2 or 3 different nice topological results, and all of them followed by using the machinery of the fundamental group. We'll continue talking about the fundamental group next time.